Hi everybody, welcome back to this YouTube channel. Thank you very much for joining us once again. So we are still continuing with revising your trial exam papers, and we're going to look at the 2024 pre-trial exam from Limpopo province. Okay, so we're going to look at this question on calculus. So if you're new to the channel, please guys make sure you have subscribed and just turn on that notification bell so that you can be notified every time when we upload a new session. Without wasting any time, let's get into it. All right, quite an interesting question on your calculus section. So we are given that the parabola in the figure below, right, represent the curve of f prime of x, right? So you know that this is the what? The derivative of the cubic function f of x equals to ax cubed plus bx squared plus cx plus d. Okay, guys, we have to be very careful and listen to this first statement, right? The parabola here is a what? Is the first derivative of our cubic function. You do know that in a cubic function, the first derivative will give you a parabola, right? Second derivative a straight line, like that, right? But we do need to understand some properties of this first derivative. How is it connected with the cubic function, right? Let me just draw for you maybe a cubic function like this, right? How is the first derivative connected to the cubic function? In two ways, right? Maybe three or four ways, right? Firstly, we know that at the turning point of a cubic function, this is f of x, right? The first derivative, first derivative is equals to 0, right? First derivative is equals to 0 at the turning point of the cubic function. It means when you go now and solve for those x values, right? Those x values of or the x-intercept of the first derivative will now give you the x values at the what? At the turning point. Okay, so that's how it's connected. Secondly, we do know that when the first derivative is greater than 0, that is, it's positive, then we know that our cubic function f of x will be what? Will be increasing. Okay, and we do know that when this first derivative is less than 0, that is when it's negative, our f of x, our cubic function, will be what? Will be decreasing. Okay, again, we do know that at the point of inflection, right? So the x value of the point of inflection, right, the point where the cubic function changes its concavity, is the same as the x value of the turning point in the first derivative. Okay, so at the turning point, the x value at that turning point, it's actually the x value of the point of inflection. Okay, so those are some of the things that you must be remembering in connection with the first derivative and the cubic function. All right, let's go and answer this question. 9.1. So in 9.1, it says write down the gradient of the tangent to f of x to the point where x is equals to 0. Okay, so they are saying what is the gradient to a tangent to f of x? That is now your cubic. Whatever is drawn here is the first derivative, right? And we do have an understanding that the first derivative is actually the same as the gradient, right? That is it. So they're saying write down the gradient of the tangent to f of x to the point where x equals to 0. Okay, so when x equals to 0, what is the first derivative is equals to? Because we do know that the first derivative when x equals to 0 will give us actually the what? The gradient of the tangent to f of x, which is our cubic function. Okay, so what is the first derivative when x equals to 0? This is x equals to 0. You know, at this point we have 0 and 4. Can you see the first derivative is equals to 4? So we do know that the gradient will be equals to what? Will be equals to 4 when x equals to 0. Okay, when x equals to 0, what is the first derivative? First derivative is 4. And we know first derivative is the gradient. So that's why it's 1 mark. So it's just for you take it from your graph. It's your y-intercept there. X equals to 0, y equals to 4 on the first derivative. That is it. Let's go to 9.2. 9.2 is saying, write down the x coordinates of the turning points of the curve of f of x. Okay, what are the x coordinates? What are the x values of the turning point of the curve f of x? You are drawn the first derivative, but they want the x values of the turning point of that cubic function using your first derivative. What do we know? We know that when the first derivative is equals to 0, the x values, right, represent the x values or the x coordinate at the turning point of our cubic function, right? In other words, the x-intercept of the first derivative will give us the x coordinates of what? Of the cubic function. Okay, so let's just go and observe what is the x-intercept of this cubic function that is drawn here. We can see the x-intercept is x equals to 1 or x equals to 3. These are the x-intercept of this first derivative, and these are actually the x coordinate on the turning point of the cubic function. Hence, it's just 2 marks. Okay, 9.3. For what values of x is f of x strictly decreasing? For what values of x is f of x strictly decreasing? We have discussed this. When f of x is decreasing, what happens? How do we know that f of x is decreasing? Our cubic function is decreasing when the first derivative it's actually less than 0. Okay, when it's negative. So we are going to observe at which x values is our first derivative below 0 or negative. Okay, because that is the interval at which our cubic function will be increasing. All right, so let's check for which x values is f of x below 0. You can see f of x is below 0 from this point, from x equals to 1 to x equals to 3. Can you see it's below 0 here, right? That is your first derivative here. It's below 0. It is negative. It's on the negative side. Can you see? So we can see where when the first derivative is less than 0, our graph, it's actually the cubic function will be decreasing. That is when x is between 1 and what? And 3. So this is the interval at which you will find f of x strictly decreasing. That is when the first derivative is below 0, when it's negative. All right, let's go to the last question. 9.4, it says show that x equals to minus b over 3a is the x coordinate of the point of inflection of f of x. Very, very important. Show that x equals to minus b over 3a is the x coordinate of the point of inflection of f of x. Okay, what do we know about the point of inflection, guys? We do know that at the point of inflection, the second derivative must be equals to 0. Okay, it means what we can first do is we'll first go and find the first derivative, right, using this cubic function. So the first derivative, let me just write it there on top. First derivative will be equals to 3ax, 3 minus 2, it will be squared, plus 2bx, 1 minus 2 minus 1, who left with exponent 1, plus cx, 1 minus 1, it will be 0, then x exponent 0, this is 1. Okay, so that will be our equation of the first derivative. Then our second derivative, because we are talking about the point of inflection, Second derivative will be 3 times 2, 6a. X exponent 2 minus 1 will be left with 1 plus 2b. X exponent 1 times 2b, it will remain to be 1 minus 1, it will be 0. This is a constant derivative of constant is 0, and this will be exponent 0, then this will be 1, then we'll just be left with 6ax plus 2b. All right, so we do know that at the point of inflection, the second derivative must be equal to 0. So I'm just going to take this first derivative, which is 6ax plus 2b, and equate it to 0. Then I solve for x. Okay, so it will be 6ax is equals to what? Is equals to minus 2b. Then I divide both sides by what? By 6a divided by 6a. Okay, so therefore finally x will be minus 2 over 6, which is minus 1 over 3 b over a. Okay, so we have actually shown that indeed at the x coordinate of the point of inflection will be minus b over 3a. All right, I hope you find this helpful. Don't forget to share, like, comment, and subscribe. See you soon. Bye.